Sharing and go directly into this full screen. Okay, so can you guys assure me that you all have that diagram in front of you, right? So what you're looking at, let me just go over it before we start even talking about it. What you're looking at is, they call them single-phase transformers banked together to make a three-phase system. Like I told you guys before, you can have, you can get three-phase system two ways. One way is to have a three single-phase transformers. Here's one, two, three. Hook them up Y or delta like this, delta Y or YY or delta delta, and that will get you three-phase system. Or you can have the big fat fluffy three-phase transformer built in. So as if they put all these guys, single-phase transformers, as, instead of one standalone device, they put it as a coil. Coil 1, coil 2, coil 3, built into a three-phase transformer. That's the most common one. This one, you're going to encounter a lot. Utilities use this a lot, as well as if you have industrial, when we're doing industrial. You could see this one in an industrial plant. Commercial building, you wouldn't see it. But what we're doing, Adam, we're doing industrial, right? So this could, you could encounter this situation. Okay, so what I have, guys, I have three transformers. Each one of them is 75 kVA, 1, 2, 3. I hooked them up delta Y, typical. The delta is 13.8 kilovolt, and the Y is 482.77, right? We have a neutral. We have phase A, phase B, phase C, and a neutral. On the secondary, on the primary side, we only have three phase, no neutral. Why? Because it's a delta, right? It's a delta. And we need to answer all these questions. Like I said, this will be on the test, guys, as well as on the final. So we're going to answer these a few questions. Number one, any question about what we have? Yeah, and we have Z. You guys remember what Z is? The impedance. Z is the impedance. It's given as 6%. So we have a transformer 6% impedance for all this system. And we need to find a bunch of things. I think 16 things we need to find for this system. 16 things. Okay, the first thing we need to know is something called, if you can't read my handwriting, because I tend not to be able to read my own handwriting sometimes, so please, no hard feelings. Let me know so I can read it for you. Okay, here's what we have. We have banked KVA system. Banked KVA system, guys, we have three transformers. When you bank them together, what's the total KVA of the system, right? Anybody? Just add them up. So the banked KVA system, gentlemen, is you take the three, because three of them, and multiply it by 75, and that will give you, gentlemen, 225 kVA. Done. Here's your banked system. Any question about that? Add them up. Where does the 3 came to be? Here's 1, 2, 3. Where is the 75 came to be? Here's 75 kVA, 75 kVA, 7. Add them up. Done. Okay, the second thing is V voltage. V is voltage. V, P for primary. This side is called the primary, as you know. L is for line. Everybody understand what that VPL? VP is for the primary. L is for the line. Cool? L is for the line. VPC, P is primary, C is for the coil. The coil and the line voltage. The line voltage and the coil voltage. Okay, V primary, here's a primary. What's the voltage of the line? The voltage of the line, map, is the voltage between phase A and phase B, right in here. What do you guys think the voltage for the line? You're looking at it. Anybody? Right there, 13.8. The voltage for the line voltage is 13.8 kV. Cool? That's it. 13.8. You're looking at it. Now, voltage V primary for the coil. Here's the coil. Can you guys see? I'm going to draw the coil right in here. Here's the coil, and here's the coil. The voltage right here. Matt, do you see that the voltage between these two is identical to the voltage between these? It's the same. There's nothing in between them. The voltage only changes, guys, if there's a load between them. Do you see any load between this point and this point? Any load? Load, not fuse, not wire, load, as in a transformer or a motor. Nothing. So the voltage between these 2 points and the voltage between these 2 points are the same. The coil voltage and the phase voltage are the same. Okay, so this is also 13.8 kV. Done. 13.8 kV. Any comments, guys? Any questions about that? See how easy it is? Just looking at it, identifying it. And I do this one time, Karen, and I move on. This is, I don't mix as we move on. We start talking line and coil voltage. You understand what the line and the coil. You guys have heard this before, right? A lot of you have heard it. And when you go to next semester, math, we'll go into details. And I know you skipped one semester. Okay, V. V, S for secondary, L for line. Here's the secondary, the line, phase A to phase B. What's the voltage between phase A and B? It's always the highest voltage. When you have two voltages, the line voltage math is always the highest voltage. So the line voltage here is 480, right? 480 volt. Everybody understand the K? There's in the primary. Okay, so that's my voltage on the primary. Voltage in the secondary, for you guys, you skip it to the right side on that sheet I gave you. Okay, so that's V secondary. How about V secondary coil? Here's the coil. Can you guys see the coil between the neutral and the phase? What's the voltage between the neutral and the phase? You guys know that, the lower voltage, 277, right? Okay, so I'm going to go to next one is V secondary coil. That will be 277. 277 volt. Done. All right, now I primary line. By the way, I put a star next to anyone that I put a star next to. You guys have that red star? You guys see these? When I put a red star next to it, this means that voltage is very, very important. We use it all the way for calculation. One more time. Where I put the stars here, this means these voltages that we have calculated are important because we use them to calculate the current. And we use them for sizing the equipments and what's not, which is basically the line voltage. Okay, V primary line, VP primary line, the line current. The line current, gentlemen, is the current that's coming right from in phase A, phase B, phase C, hooked into this transformer, transformed to this side as also A, B, and C at different current and different voltages. The current that's going through phase A and phase B and phase C through the lines. Okay, what's the other, the coil current? The coil is the current that's going right here. Can you guys see that? The current that's going right through the coil here is called the coil current. This current is line current, coil current, line current, coil current. On the primary side, they're different. On the secondary side, they're the same. Look at this. Here's the coil current coming out of here all the way. It becomes line current. One more time. Coil current, line current. Aren't they the same? In a Y, the coil current and the line current in a Y are identical. Current goes and it starts as a coil and becomes a line. In a delta, it's different. It comes here as a line, then it's split here as a coil. Cool? Everybody understand that one? Okay, so now let's go find the V primary line. V primary line, guys, piece of cake. You take the kVA, which is 225 kVA, divide them by 1.73. Everybody understand why 1.73? That's a component of the three-phase system. And what's the primary voltage, gentlemen? Line to line, 13.8 K. When you do a problem like this, Adam, the easiest way is the K, cancel the K with the K, right? You guys can see this, the K's cancel with each other, right? Because KKF becomes 225 divided by 1.73 multiplied by 13.8. Because there's K at the top and the bottom, these cancel with each other. Gentlemen, you got yourself a healthy 9.4 amps. And when you have high voltage math, you're going to end up with a ridiculously small current. That's the advantage of having high voltage. So you can shoot that tiny little current all the way to Texas and no voltage drop. It's easy to shoot a tiny little current. Bigger current, what happened? You need interstate width. It's a conductor. So that's why we like the higher voltage, because it gives us always lower current. Okay. How about I secondary? I secondary line. I jumped into the secondary line and I put two stars next to them because these are very important. We use them to size fuses and conductors. Okay, we're going to use the same thing, 225 kVA divided by 1.73 times. What's the voltage line to line? The voltage, guys, line to line on the secondary side. 480. gentlemen, if you did your math like your free chat, you'll end up with 271 amps. 271 amps. So on the secondary side, you have 271 amps. On the primary side, you have 9.4 amps. Cool? I want to bring to your attention that little red star here. When you find the current, you always use the line-to-line voltage, the line voltage. We don't use the coil voltage. Did you guys hear me? No coil voltage. Okay, so now let's go find, that's why I put these two. These 9.4 and 271 atom, these are the ones that are going to size your conductors and fuses. The coil current, we don't use them a lot. Just FYI, basically. Okay. I primary coil. The primary coil, guys, the formula is equal I primary line divided by 1.73. Piece of cake. That will be 9.4 divided by 1.73. And that will get you a healthy 5.4 amps. Ridiculously small amps. 5.4 amps. See how easy that is? Very easy, simple. On the secondary side, gentlemen, the same thing. I secondary line divided by 1.73, and that will get you 271 divided by 1.73, and that will give me a healthy. Oh, I'm sorry. On the secondary side, now I lost it. On the secondary side, it's a Y. I forgot that's a Y. On the secondary side, guys, it's a Y. It wasn't a delta. I forgot that it's a Y. On the secondary side, can you guys see the current comes as a coil and moves back as a line? Does it change itself? Is there any change in it? No. So on the secondary, because it's a Y. In the secondary side, I secondary coil equal I secondary line equal 271 amps. And your explanation, because it's a Y. I put that Y connection. That's a Y connection. It's not a delta. The delta they changed. The Y doesn't. Any comments, gentlemen? Any questions? Any comments? Any questions? If you came from the electrician program, you guys go this in the second semester. We do that one. This will be probably repetitive for you. Some of this stuff. Any comments, gentlemen? See how easy that is? Really not hard. The ones that I put star next to them, Karen, are so important because we'll use them to size the fuses and circuit breakers. Okay. Moving on. Now there's something called transformer ratio. Transformer ratio, gentlemen, is defined as voltage primary coil over voltage primary secondary. Voltage primary coil over voltage secondary coil, coil to coil. Okay, so we'll start with 13.8 K divided by the coil is 277. These are voltage. And when you divide these by each other, you're going to end up 50. And the ratio is going to be 50 to 1. My ratio, transformer ratio, is 50 to 1. What that means, every 50 volt on the coil of this primary will be equivalent to 1 volt on the coil on the secondary coil. Transformer ratio. There's another term that they use, the transformation ratio. Transformation ratio defined as the primary line over the secondary line. You can see the difference line to line. 13.8 K divided by 480. Remember, these are all voltages. And when you divide it by each other, gentlemen, you're going to end up with 29. So the transformation ratio is 29.29 to 1. That's your transformation ratio. What does that mean, Karen? Every 29 volts line to line on the primary side will be equivalent to 1 volt on the secondary side. If you're doing, guys, you can use them to find the current on the primary and secondary using the ratio and what's not. Any comments, guys? Any questions? Up to this one, transformation ratio, like I said, is used to find the ratios, as well as the transformer ratio, to find the ratio to find the primary secondary current from the primary secondary voltage. Primary feeder. The primary feeder, now, for transformers, guys, you're going to ask yourself the following. Is it continuous load that's going to be coming out of this transformer? I really don't know. Okay, what's the worst scenario? We're going to assume it's continuous load. How do you size a continuous load? You guys did it with me. If you know a continuous load, you always multiply it by the magic number, 1.25. So we're going to assume that it's a continuous load. We'll multiply it by 1.5. So the first thing you need to do, we need the primary. So I primary line is always the one that you use, which is 9.4 amp. Remember, the voltage is 13,800 volt. That's the feeder. I need a feeder that can carry 9.4 amps at 13.8 kilovolt. Karen, ask yourself, is it continuous load check? No idea. What's our scenario? So it's continuous load. So step number 2 is 1.25. Multiply this baby by 9.4. And if you guys do your math, it gives you 11.8 amps. Okay? And the last thing you need to do is going to take your 11.8 amps and take it all the way. Now, I will remind you, Derek, that the voltage is not 600. So you can't go to the table 310.15B16. This is high voltage. You have to go all the way to a different table. The table that you need to go to, guys, is 310 table 310.60 C77. And you need to go from NEC 2011, and you need to go under 15 kV. So 310.60 C77. I think I have it in the second column here, right? You guys have it in with you. There's the table that you're going to go to, gentlemen. We haven't done this table. I think we did part of it last semester. Why did I go to this table, Karen? Because this table have higher than 600 volts. Okay. So if you guys read through this one, and you can go to the NEC book and look at it there. This table, it has up to 5,000 here, and this is 5,001 all the way to 35. So where should I be? I should be in the 13.8 K is right in here. Then 90. I can either have a 90 or a 105 Celsius cable. Default is 90. So, and the amps that I'm looking for is 11.8. The smallest they can get is 90 amps. So what's the smallest conductor they can get out of this baby? Number 6. Number 6. So this conductor, gentlemen, is going to be 3 conductors. 3 conductors, number 6AWG. And what's the insulation type? MV90. What's MV stands for? Medium voltage. What's 90 degrees Celsius insulation? That's typically what you do. So when you, on the test, Adam, please, you're going to write me how many conductors? 3. Why 3? 3-phase. Size number 6. Why number 6? We went to the table, got it number 6. And then what's the insulation? It's not THHN, it's not THHW, it's MV for medium voltage and dash 90 degrees Celsius rated temperature. Where did I get this stuff, gentlemen and ladies? Here's the table that you're looking at. Oops, let's go back into the table. Here's the table. This is the table. 3 single insulated conductors in an underground dock. So you come over here, that's what we're assuming we're bringing him underground, right? And I can either go to these sets of columns or these. I went to these because my voltage is 13.8. Probably your quiz might be, or your test, it might be 2400. So where do you go? To the first set of columns. Then, when you're here, because of 13.8, you ask yourself, what type of insulation do I need? 90C or 105? Can I have a choice? Yes. If you don't know, what's your default? 90. So my default is 90. So can I use number 8? No. Why? They don't want you to use number 8. You go all the way to the next 90, yeah, all the way number 6. So the smallest they can get is number 6, regardless. So we'll use number 6 that can carry 60 amps, 90 amps. That's number 6, 90 amps. That's not unheard of in the low voltage. Even though we need how much amps? 11.8, because that's the smallest you can get at this voltage. Cool. Any question, guys, about this table? Am I right to assume that you guys know how to get that? This is 310.60C77. Okay, we got that? Got that, gentlemen? Okay, now we found the primary. Let's go to the secondary, gentlemen. Will you? Let's go to Mr. Secondary. Okay, we need the secondary feeder size. Secondary feeder size is 13. The way we use the first thing you need to use, guys, is for this you need to use I secondary line always, and that will get you 271 amps. That's the amp that you use. Then what you do is now add on. We're going to assume the same thing, continuous load. We're going to assume it's continuous load. So we're going to take 1.25 multiply it by 271. That will give me a healthy 339 amps. Okay, and I want to take this one directly into table 310.15B16 under 75-degree column. Why did we go to 310.15B16, Karen? Because the voltage is 480, and that's the table they use if the voltage is 600 volt or less. Gentlemen, how many conductors do I need now? If you guys go there, you're going to find the size is going to be 500 kcm. The insulation that we're using, I'm going to assume it's going to be THHN, or indoor. I will ask you how many conductors do I need. Now, at least 3 conductors, right? Phase A, phase B. You can't, 3-phase system, you have to have at least 3 conductors. Now, the question would be, would I carry the same full neutral, or would I derate the neutral? We're not derating the neutral here, so you carry, if you don't know, carry full neutral. So we're going to carry how many conductors? 4. Why 4? Phase A, phase B, phase C, 3, and a neutral, because it's a Y. Could I have derated the neutral like you guys are going to be doing with me? Yes. For the sake of this calculation, we don't want to complicate it and start derating the neutral at this time. Okay. Primary overcurrent protection devices. Primary overcurrent protection devices. Protection devices. Okay. Primary overcurrent protection devices. Fuses. I need to go fusing. For the fuses, guys, I would like to take you to the next table. So please go to the NEC code book too. The NEC code book has these tables. Here's the table that you're going to go to. This table says 450.38. This is the table that gets you the fuses for the circuit, for the transformers. Here, I will remind you, my transformer is 13.8 on the primary, 480 on the secondary. Okay. So primary protection over 600 volt, is it? Yup. Secondary protection, is it over 600 volt? No. Is it under 600 volt? Yes. Why? 480. So that's why I highlighted this side and this side. So first the primary protection over 600 volt. You have a couple of options. Supervised location. Have I told you that this is going to be in a supervised location? If they say supervised location, like in an industrial plant where people are, electricians are maintaining the system, you can size it differently. If you have no idea, you default to where? Any location. Default. Then, not more than 6% impedance. What was the impedance? Remember I said my impedance is 6%, so am I right here? Yep. Well, otherwise, where do you go? The second one. Then, are you using a circuit breaker or a fuse? What did they tell you guys? Fuse. I'm using a fuse. So what's my multiplier? 300 on the primary side. Do you guys see note number 1? If you read note number 1 here, it says, hey, if you land with a non-standard fuse, do not get mad, go up. Note number 1 is very important. It tells you, do you guys remember that note number 1 in the motors too? Or we used to have some note like this. So this note at the bottom here tells you if you don't land on a fuse, standard fuse, what do? Go up. So we're right here. Then on the secondary side, since I'm here, let's do the secondary. Is the voltage on the secondary over 600 volt? You're looking at it. No, it's not over 600 volt. Then I have to default to this column, right? 600 volt or less, yep, 480, 600 volt or less. Come over here. Same thing. So you guess the impedance, we decided impedance is the first row. So fuse or circuit breaker, my multiplier is 125. If you guys read through it, it's 125. Do you see note number 1? Yep. There's a note number 1. What does note number 1 say? If you hit a non-standard, please don't get mad. Go to the next standard. Can I leave this table, guys, knowing how to use that table? With the highlighted stuff, you guys use is colored, right? With the highlighted stuff, do it for you. So feel free to keep this one on the test. But here's what I can change it for you. I can change this voltage to 2400. If this one, 480 to 2400. So if it's 2400, which column are you going to be using? Over 600 volts, right here. So now, if it's a fuse, you have to be here. If it's a circuit breaker, you have to be here. You can see where the difference. Look at the voltages. You size them based on the voltage, as well as the impedance, as well as the location. Can I have thumbs up, Chad, that we know how to use this one, this table, with this explanation? Okay. Now, having said that, let's go directly into the 14. 14, primary overcomputation device. Okay, so the first thing you need to do, guys, is I need I primary line. I primary line, you guys remember it was 9.4 amps. Then you need to multiply it by 3. 3. Everybody knows why 3, or let's just do it 300. 300% from the table. 300% times 9.4, and that will get you, gentlemen, 300% times 9.4. Where am I here? Primary overcomputation device. 28 amps. 28 amps. Anybody has an issue with that? 28 amps. Then, gentlemen, you take that 28 amps, take it to 240.6. What's in 240.6? You guys remember these are all the standard overcomputation device, and you go to 30 amp. If it's not a standard, this is the standard, you can go up. So my fuse on the secondary side will be 30 amps. Why did I go up, Adam? Because there's a note number 1 in the table that says, hey, if you don't hit like they don't make a 28 amps fuse for you. So you can custom design yourself a 28 amp fuse, or you can go to the next step. Any comments, guys? Any questions about that? Comments, questions? Let's go to the secondary. Same thing. These tables, guys, we're using for both of them. We're using table 450.3a on the primary and the secondary side. Oh, I forgot to highlight this one here too. Okay, so on the secondary side, gentlemen, we've just looked at it a second ago. Okay, the first thing you need to do is first use I secondary line equal, it was 271 amps. Then you multiply that baby by, what is it, 125%, multiply 271. If you guys do the math on that one, you're going to end up with 339 amps. Cool. And then you take the 339 amps, take it to the same table, guys, 240.6, and that will get you a healthy 350 amp. And would I go, guys, to up or down? Would I go up or down? I go up. If it's not a standard, where do I go up? Why do I go up, Adam? Because the table tells you to go up. So 339 becomes 350. Everybody understand how to go to 240.6, guys? We have been there for non-adjustable fuses and circuit breakers. Any comments, guys? Any questions? Comments, questions? Okay, let's go to 16. Am I going too fast, by the way? Too slow? Easy? Okay. There you go. We went through this table. Make sure you know how to use it. All right, the last thing that I would like you guys to do for this particular baby is find the short circuit on the secondary side of a transformer. So Adam, you went to the secondary, you grabbed phase A, phase B, phase C, bolted them together, flip the switch. How much short circuit you're going to have? You guys have done SKM for me. That's related to the available short circuit at the secondary terminals of a transformer. Very easy. You always go to the secondary, so that will be I line secondary. Divide that baby. I'm sorry, we should write it the proper way. I secondary line. I secondary line. Secondary side line divided by the impedance Z percentage. Piece of cake 271 divided by the impedance was, what did they say, 6%? And when you guys do that one, you're going to end up with, is it 45K or 4.5? I have 4.5 K kilo amp. The short circuit is 4.5, right? 4.5 kilo amp. Karen and Adam, here's your homework number 1. That it's, you guys have it on your sheet. So we're going to have 4160 primary, same transformer, secondary 208 transformer. The kVA of the transformer, each one of them is 100 kVA. So the total would be what? The three together, 300. The impedance is going to be 2. And you guys are to repeat all these 1 through 16 for this transformer. Not now, of course. Shall we flip to the second? Everybody see that homework number 1? So if I were you guys immediately get into it, step by step you can see it. So you guys need a quick break, or should I roll into the second? Quick one? Okay. Any comments, any questions? So I'm going to have 2 more examples like this, and then we're done for the transformers. Okay, let's have a quick break. Here. All right. So here you go. Right on the money, man. That's all right. So you got the homework, guys. Let's go directly into the second one. You have a picture of this. I picked this one for you, Adam, for one reason, because this one has primary and the secondary voltages are less than 600 volt. Can you guys see that? The primary is 480. The secondary is 208, 120. That's the reason why I picked this one. By the way, all the steps are identical. Identical, almost. So 3 single-phase transformers. Each one of them is 50, 50, 50. They are hooked up on the primary side as a delta. On the secondary side, they are hooked up as a Y. Can you guys see the connections? There are 3 phase on the secondary, plus and neutral. On the primary, there are only 3 phase, no neutral. Can you guys see that? The impedance of that baby is 5%. The primary voltage line to line is 480. And Matt, can you see the same thing also? Line to the coil voltage is also, the coil voltage is 480. On the secondary side, the line voltage is 208. The coil voltage, which is the voltage between the coil here and right in here, this voltage is 120. Cool? Any comments, any questions about what we have? You guys see what we have? 480 on the primary side, on the secondary 208, 120. 3 single-phase transformers banged together to each one of them is 50 to make 150 total. And we are to find the feeder size and the fuses on the primary and the secondary. So any question, guys, before we flip into the process? You're going to see repeating itself. Let's go to the band. So now the rest of them, guys, will be very easy now. You're going to see. So this one will be 3 times 50 Adam kVA, and that will get me 150 kVA. Done deal. Everybody knows why 3, because it's 3 transformers. Why 50? Each one of them is 50. Okay, primary line voltage. So primary line voltage right here. The primary line voltage on the primary side is 480, guys, right? 480 volt. That's my primary line voltage. Primary coil voltage, it's a delta. So what happened in a delta, guys? The line voltage and the coil voltage are the same. So on the primary side, it's 480 as well. 480. So 480 line and coil. So I like to write it this way, actually. So it keeps reminding us V primary line equal 480 volt, and this is my voltage. Secondary line voltage. Secondary line voltage, guys. Line voltage. Adam, what was it? Line to line, 208, right? Is 208 volt, the highest voltage. How about secondary? Oops. How about secondary coil voltage? Secondary coil voltage, guys, equal, if you want to do the formula for it, equal V secondary line divided by 1.73, as a matter of fact. And just by looking at it, you're going to find it's 208 divided by 1.73, and this will get you V secondary coil as 120. If you guys do the math, which is already shown. The V secondary voltage is 120. Cool. Any comments, any questions? Straightforward, right? Yes, no? Straightforward. So let's go directly into the second one. A primary line current. For the primary line current, primary line current, you're going to have the kVA. You take the kVA divided by 1.73 times the V primary line. That's your formula. So you remember it was 150 kVA divided by 1.73 times 480. Gentlemen, and you get yourself a healthy 180 amps on the primary side. Secondary line current, same thing, 150K divided by 1.73 times 208. That will get you on the secondary side, gentlemen. Primary, okay, so where are we here? Secondary line current, we got yourself, yep, 208. That will get me 417 amp on the secondary side. Any comments, guys? Any questions? Repeat, or I'm going fast because it repeats itself. Okay, primary coil current. Primary coil current, guys, you remember that we said I primary line divided by 1.73, right? The coil current, and that will give me 180. Divide by 1.73, and that will get me a healthy primary coil, 104 amps. That's my coil current. Each coil is going to be carrying this. On the secondary side, secondary line, coil and line are the same, so that will get me a 417 amps in both coil and line, right? Because it's a Y. Any comments, gentlemen? Any questions? Ladies and gentlemen, any comments, any questions? See how easy it is? The confusion that a lot of people guys have is they don't know what the primary and the secondary, get confused. So please, please, between the homeworks and what we do this, hopefully that will get you the side of the transformer. Any comments, any questions? Should we go to 10? When you have a chance? Make sense? Karen, good? Okay. All right, transformer ratio. Transformer ratio, we talked about this one, guys. The transformer ratio, we see V primary coil over V secondary coil. And you take the 480 divided by 120. That will get you a healthy 4. And if you convert this one, it becomes 4 to 1. That's your ratio. 4 voltages on the primary coil will equal to 1 voltage on the secondary coil. Transformation ratio, V primary line over V primary, V secondary line, line to line, secondary line, line to line. So they'll get you 480 divided by 208, and that will give me a healthy 2.3, and that will get you a 2.3 to 1. That's the ratio line to line. The ratio line to line. That's your ratio line to line. Straightforward, no gimmicks, nothing. Okay, primary feeder size. Let's go size the feeder. Shall we? Size the feeder. Are you guys good up to this point? Straightforward, the ratios? Yes, no? Too fast, Chad? Slow down? Too much coffee? Okay. On the primary feeder size, we just talked about this one a second ago. So you need to go I, primary line. You guys remember the primary line, I primary line 180 amp. So all what you have to do then, 1.25 times 180. We're assuming it's continuous load. And we're going to come up with 225 amp. Take this one, gentlemen, to table 310.15 B16 under 75-degree column. Why did we go there? Why didn't we go to the other table, the C77, guys? Because the voltage is 480, right? The voltage is 480. If you guys go there, you're going to end up with 3 conductors for the 3-phase, 4-aught, AWG, and the insulation, let's assume it's going to be T, H, H, and dry location. We're in the dry location. Here's my conductor size. Here's my conductor. Any comments, any questions about the primary? Why did we go to this table, Derek? Because look at the voltage, 480. So we don't have to go to the special table that the medium voltage conductor. It's not my medium voltage conductor. Okay, secondary feeder, gentlemen. For the secondary feeder, we're going to do the same thing, gentlemen. I, secondary line, equal what? The secondary line for this one was, what was it, 417? Anybody can remind me here? 417, right? Yeah. 417 amps. Okay, what do you do? 1.25, multiply that baby 417 equal. That one will equal 5 to 1, if I did my math right. 5 to 1 amp. And then, I know I told you guys, Derek, I told you if you go higher than 400 amp parallel, right? Just for the sake, I don't want to parallel this time, but typically you parallel. Anything for, this is 521, a lot of amps. We parallel. So for this one, I just want to go straight shot, 421. If you go to table 310.15 B16, 75-degree column. Gentlemen, for conductors, each one of them is 900 kcm. T, H, H, and assuming dry location. Assuming dry location. And we're not derating the neutral at all, which typically we do. And this is not a good design, by the way. This is just for calculation. What would you do? In the primary, is there a neutral? Remember, it was a delta? See, you always keep an eye on the, there is no neutral. If there is one, it will be a fourth. Typically, the neutral will start derating them, guys. You'll see. But for the sake of the calculation, if you put it this one, you got your calculation. Any comments? Any questions? So this is an easier one. We go to one table. Karen, good. Go to next one. Everybody. You guys write faster than I do, or am I slowest kid here today? All right. 14. Primary overcome protection device. 14, primary overcome protection device. Now, for the primary overcome protection device, I want to go to this table. You guys have this table, right? This is table 450.3b. The one that I showed you here was 450.3a. You use A if the primary or the secondary or both was higher than 600 voltage. You use B if the primary and the secondary are, both of them, 600 voltage or less. So can you guys look at my transformer? I have 480 on the primary, on the secondary 208. Does this table apply to it? Yep. Are the primary and the secondary less than 600 volt? Yep. So this is your table, 450.3b. When you go there, primary protection. So and secondary protection. So let's start with the primary. Current over 9 amps or more. Do I have more than 9 amps on the primary side? Yeah, was more than 9 amps. So I'm here. Then you have primary only protection. You only put wind protection or primary and secondary protection. You default primary, secondary protection. And so what's your multiplier? 250. Do you guys see note number 1 here? There is note number 1 here, so you have to go down. There is no. Come on the secondary side. Are you using, is the current more than 9 amps? Yep. So here's my default. 120. Do I have note number 1? Yep. So do I go, what do I do? I go up here then, and I go down here. Can you guys see that? Down on this side, because there is no note number 1 here. Or is it? That's not number 3, I thought. Is that not number 3? Yeah, should be. Not number 3. Yeah, number 3. So you go down here and up here. Can you guys see that? Any question about this table? One more time. Look at the voltages. Will lead me to this table. Where I have 2 rows. I should pick between the 2 rows. Typically, primary, secondary protection. So I go to the primary and secondary, not the primary only protection. Then my 2 options are: is my current more than 9 amps or less than 9 amps or less than 2 amps, right? Look at your current. Your current is definitely here. So you're here. Same thing here, secondary. Is my amps more than 9 or less than 9? More than 9, so my default is here. Do I have note number 1 to go up? Yup. Do I have note number 1 to go up? No. So I have to go down. Cool? That's the table that we use for when the voltage is both on the primary and secondary resistance 600 volt. Okay, let's go do the calculation, gentlemen. Number 14. Number 14. So step number 1, I primary line. You're going to start with always the primary line, gentlemen, which is 180 amps. So what's my multiplier? My multiplier 250%. Multiply 180. Gentlemen, it gets you 450 amp. Okay, 450 amp. And then take this one to table or article 240 section 6, and that will get you, if it's not a standard, you are to go down, but it is already a standard. 450 is a standard. So we hit the jackpot. Basically, we hit the jackpot. We don't have to go up or down. But if we were 449, we have to go down to what? 400, not up. Can I emphasize the word down, guys, on the primary side? Secondary side, gentlemen. Same thing. I secondary line equals what was 417 amp. My multiplier, gentlemen, was for the secondary side 125%. Multiply 417 and get me a healthy 521 amps. Take this baby into 240.6, and when you go there, 240.6, it will get you 600 amp. And what do you go? Do you go up or down? You go up. Why do you go up? Why do you go up, gentlemen? Because there is a note number 1. We just looked at it. There is note number 1. Okay. The last thing, gentlemen, we need to find the short circuit at the secondary, which is piece of cake. You take I short circuit equal on the secondary I secondary line divided by Z percentage, and that will give me 417 divided by 5%. And when you do that, gentlemen, you end up with 8.3 kiloamp. Any comments, any questions? Piece of cake. Or not? Yes? Piece of cake? Almost. Piece of cake. So I know, Karen, there's a lot of ups and downs and what's not, guys. Here's what I would like you to do, Derek. Write yourself a note about transformers, have him say on the primary side, go up, down, write it on your sheet. I get confused, guys. There's so much. By the time we finished, we're going to be talking about fire pumps and generators and auto transfer, tons of stuff, and PDUs. By the time we finish all this calculation, if you are not confused, you're not with us. So the way I stay sane myself is I write myself a note. See that sheet here? If I don't have that sheet, I have to rethink the whole problems again. There's so much. That's why I give you these sheets, guys. Have them as a reference. Write all this info with you. And then on the test, bring it with you. I have no problem with that. Because it just says so much, especially for the final. Okay, can I move into the next problem, guys, gentlemen? Yes? Okay, so remember how to use this table. Here's my table. We went over that one. Okay. Example number 3 and the last example. I don't have homework for this particular one because it's similar to the one that you guys have did. The only difference was the voltage. Okay, this guy is different. This transformer, Karen, is a delta center tap. Can you just see that center tap right in here? Yeah, Mr. Center tap right in here. Delta center tap. Since you guys now are industrial guys, and we're doing industrial now, not commercial anymore, you will see this one by utilities in an industrial plants or certain applications. Here's what they do, Karen. They take 3 transformers, but this time they're different sizes. 2 of them are the same, and 1 big fat boy. 2 skinny ones, 100 and 100, and a big fat boy. Can you guys see that? Now, and from these systems, they created a delta center tap, which is 24120, used in the US. 24120. Why? So that big boy here, I'm going to highlight it here. This guy here, this transformer is the 150K. The rest of them are 100K. This will be my 100K, and this would be my other 100K. Okay? So anybody knows why they put one of them becomes bigger than the others? Because this transformer here will be seeing the 3-phase as well as the single-phase load. 3-phase and single-phase load. They use this system, guys, 24120 to get you 3-phase 24120. It's the only way you can get 3-phase 24120. You can get single-phase 24120, but not 3-phase. To get the 3-phase Karen 24120, when you become a project manager, go to the site and they say, well, we have 240, 120 3-phase. The first thing must come to your mind, it's coming out of what? A center tap delta. They call it center tap. They go to the guts of the transformer, pull over wire, 1 transformer, which is that boy here, and they pull a wire, and that grounded, and they pull the neutral. So you get phase A, B, C on the secondary with a neutral. On the primary, you get 3-phase. Can I get you guys to understand this is used only to get 241 phase? With it, there's the wild leg. Remember that B? Where's phase B? Phase B, the wild leg, the voltage between the neutral and B is 208, not to be used. We don't use that voltage. Okay, so, and I have a panel. I have a couple of ABC, the panels here. So they have 240 single phase, 243 phase, and 120. So from this panel, guys, you can get 3-phase 240. You can get 120 between phase A and the neutral, C and the neutral. You can get 240 single phase between any 2 phases. But to get 120, the only way you can get 120 from this system is if you go to phase A and a neutral, or phase B and or phase C and a neutral. B and a neutral will not get you single phase. It will get you 208 wild leg, not to be used. And this, typically, guys, this is orange, will be labeled orange, and it's called the wild leg, not to be used for single phase. Any comments, any questions? So out of this system, I can feed 3. I can feed 3-phase. Here's my 3-phase 240. Done. How about my single-phase 240? No problem. How about my 120? 120 is only coming from A to neutral or C to neutral, not B to neutral. Can I get you guys that one? Understand? Because B to neutral will get you to 8. Okay, comments, any questions? Any comments, guys? Any questions about that? So that's why I have this load here. Can you guys see it's coming from phase A and phase C, but not phase B, the 120. Okay. Any questions about the system? As long as we're on here, guys, can you guys see the line voltage and the phase voltage here and the core voltage are the same here? Here, the line voltage and the phase voltage are the same, except we have two phase voltages in a second. All right. Questions about that system? Why do we use it? To get us 241/23 phase. The only way we can get three phase 241/20. All right, gentlemen. Let's talk about, now we have two KVAs. We have one called three phase and we have one called single phase. Okay. So the three phase KVA, you can look at it. You take basically 100K plus 100K plus 100K, and gentlemen, you get yourself 300K. This 100K, guys, this one here is actually coming from the 150. Remember, one of them is 150. You only take 100 out of it. Okay? That's it. That's your three-phase KVA. Your three-phase KVA. So you take the 100 plus the 100, and you take only 100 from the 150, only 100 to match the other phases, and that will be your three-phase. Okay, single phase. The single phase, you can get the single phase, guys, by taking the 150. So remember, Derek, we already took 100 out of the 150 for the three phase. So I subtract 100 out of that. What do you guys get here? 50 kVA. Now this is the single phase load. This transformer has a capability of delivering up to 50 kVA single phase. What does that mean? All your 120 loads cannot exceed 50 kVA. All your line-to-line loads cannot exceed 300. Did you guys hear me? Now we go by the type of the load. You have to understand, guys, in a three-phase system, you have three types of loads. So you can tie to a panel like this. Phase to phase to phase, that's called three-phase load. Phase to phase to phase, three-phase load. The second type is phase to phase. That's single phase, line to line. And the third one, guys, is phase to neutral. The phase to neutral is only 50 kVA. The phase to phase, or phase to phase to phase, is 300 kVA. That's how you can get out of this transformer. Okay, I'm showing here the example, guys, where you can take from phase by phase A, here's your load, and also from phase C. Can I take anything from phase B? I can't take anything from phase B to the neutral. Can't. It's called the wide leg. To the neutral. But I can't take another load. Look at this load. What if I have a load three-phase here? If I have a three-phase load, look what happened here. You can come feed it from phase A, from phase C, phase B, and also phase, this is my three-phase load. Phase A, B, and C, no problem. Can you guys see that? Now, what happens if I have two-phase or two huts? No problem, Chad. Come over here. Here's from B and from A and B. No problem. This is single phase. How am I going to say that? 240. This is single phase 120. This is also single phase 120. You see the difference between this is single phase 240, this is single phase 120. The 120 is only coming from A and C. I can't emphasize this enough. Any comments, guys? Any questions about that? You see why I picked this one? Because there are two KVAs, one for the three phase, one for the single phase. Okay, so let's go down. Now we know that. Let's go to V primary line. Let's go fill this information. The primary line voltage is 2400 volt, 2400. Done. V primary coil, same thing. V primary line equal 2400 volt. Done. V secondary line. V secondary line, gentlemen, the V secondary line is, the line to line is 240 volt on the secondary side. V secondary coil, there are two voltages on the secondary. there is 240 volt. That's the first one. And the second one is 120 volt. That's the second one. Can you guys see that? There are two voltages on the secondary. Let's go back to this transformer. Right? Look at this. I have one coil will have 240, and one coil here will have 120 and 120. It's kind of weird. Some of them have 120, and for a total, if you add two 120s together, what do you get? 240. So the coils, even though it's a delta, the coils are 240, plus also there is a coil 120, 120. Cool? Okay, so let's go to, this is piece of cake. I primary line, three phase. Now I primary line, guys, there are two lines on the primary, Karen. There's, on the primary line, there's current coming out of the three phase and current coming out of a single phase. Okay, let's do the three phase. So Derek, do you remember the bank, the three phase bank? What was it? 300. Thank you, 300. So you take the, this one will be kVA three phase divided by 1.73 times V primary line. Okay, let's do that. That would be 300 K divided by 1.73 times 2400. Gentlemen and ladies and gentlemen, that'll get you 72.3 amps. 72.3 amps. That's your single phase. Now, whom am I going to pick up? Matt, can you give me what the kVA for single phase? kVA for single phase? 50. Yep. Thank you. Divided by V primary line. V primary line. Okay. Is there 1.73 here? Right here. Single phase. Is there 1.73? No. For this, there is nothing because we're doing single phase. This one, yeah. So this becomes 50K divided by 2400. Gentlemen, get you a 21 amps. So I have a line, a current that's coming out of the three phase and a current that's coming out of a single phase. So what do you do, guys? The same conductor, guys, have a current that's coming out of the three phase and current that's coming out of the single phase. You know what happened to them? Adds up. You add them up. When you clamp on the ammeter, it will read both of them. Add them up. Okay. Now, phase A and C, gentlemen. Phase A and C. Current in phase A and C. Let me remind you, phase A and C, right here. Do you guys think phase A and C will be seeing the A and C? Don't you think that they will be seeing the single phase and the three phase? Yup. How about phase B? Would the phase B see that single phase? No, nothing connected single phase to it. So the tricky one here, look at that, how the tricky one. For phase A and C, what we do, guys, is we take the 72.3 plus the 21. So phase A and C will have 93.4 amps. Did I do my math right? You just 93.3. I know I have 93.4. 93.3. 93.3 amps. Cool. I think it's. Now, Adam, now if you go to phase B, gentlemen, phase B is only going to have 72.3 amps plus 0. Is there anything coming from a single phase? Nothing. So that will get you 72.3 amps. Can you guys see that? Now I have two phases carrying more current than the third one. Okay, what's wrong with that? Can you guys see that? Because two phases are seeing the three phase and the single phase, and one phase, the B, is only seeing the single phase. I'm sorry, the three phase. So on the delta side, here's my delta. is my phase A, B, and C. So this is, the current here will be 93.3 amps. The current here will be 93, this is C, 93.3 amps. What do you guys think the current here would be? 72.3 amps. Can you guys see that? If that helps you understand why, because we're using that center tap delta. One of the transformers bigger than the others. Okay, so remember these values, guys, because these values are going to be using to size the fuses and circuit breakers. In a second, we're going to be sizing the fuses and the conductor using these. I'm sorry, these two values for the phase A and phase C and phase B. So Adam, you go to a transformer, you can find 3 conductors are big fat and the other one is smaller. And you wonder what the heck is going on here? Why these 2 conductors are big and 1 conductor is small? Remember, 2 phases are carrying more current than the 3rd phase. That's only happening in center tap delta, guys, for the most part. Okay, let's go to the secondary. Same thing for the secondary, guys, gentlemen. For the secondary, I secondary, so current that will have same thing, 300. Let's use right here. Continue with using current. 300 K divided by 1.73. On the secondary side, gentlemen, the voltage is 240, and that will get you me a healthy 723 amps. For the single phase now, it's a 50K divided by the voltage is 240 volt, and that will give me a healthy 208 amps. 208 amps. Can you guys see that? 208 amp single phase. Now, Adam, phase A and phase C, phase A and phase A and phase C. I'm going to highlight these. The current in phase A and in phase C, it will be 723 plus 208 equal, gentlemen, 931 amps. That's the phase in A and C. Now, the current in phase B will be 723 plus big fat fluffy 0, and that will get you 723 amps. Any comments, any questions? Any comments, guys, any questions? I can't emphasize, guys, these are the amps they're going to be using to size the fuses and the circuit breaker. These are the amps they're going to be using to size the fuses and circuit breaker. So that's why I highlighted them in the standalone sheet. Moving to number 8. Any comments, guys, about number 6 and number 7? Number 6 and number 7 are really the hardest one to kind of understand because there's 2 components. One single phase, one 3-phase. Rest is history. Transformer ratio, guys, primary coil over coil, which is 2400 over 240. That will get you a healthy 10, and the ratio will be 10 to 1. Okay. Transformer ratio. If you do the transformation ratio, will be also the same. Will be 2 transformer 241 will be the same, right? For this particular one, you can also have another transformer ratio 240 to 120, right? Because it was also 120. So 2 transformer ratios for this one. One of them will be 10 to 1, and the other one will be probably 20 to 1. So let me just do this one here. Another transformation ratio, guys, is 2400 divided by 120. That will give you 20, right? Am I doing it right? Yeah, 20. And that will get you a 20 to 1. Can you guys see that? That's for the other coil that has 120. So the side that has 120, there is transformation of 20, or transformer ratio of 20 to 1. The side that has 240 only, 10 to 1. The transformation ratio would be, if I didn't calculate it, the transformation ratio would be exactly like this. Okay, let's go size. Number 9. Let's go feeder size, A and C plus B. Feeder size. Let's go size, feeder size, A and C. I'm going to go feeder size, A and C. And then we'll do B. A and C. For A and C, gentlemen, the current for A and C, I primary line for A and C was 93.3 amps. 93.3 amps. Cool? Okay. Then what do you need to do? You need to go multiply this by 1.25 times 93.3. That will get you a healthy 117 or something like 117 amps. Take this one, gentlemen, to table 310.60 C77 under 5K and 90-degree column, right? 90-degree column, that's a table. And we'll end up with 2 conductors. Each one of these conductors is number 2 AWG, and it's medium voltage -90. Why 2 conductors, Karen? Because we're only doing phase A and phase B. Phase A and phase C. Now let's do phase B. So for B, guys, the I primary line for B, I primary line for B was 72, only 72 amps. Then same thing, 1.25 times 72 only. That will get me 90.4. And gentlemen, if you take this one to the same table, table 310.60 C77, 5K, 90 degrees Celsius. You go to the 5K column, 90 degrees Celsius. You're going to end up with one conductor, number 4 AWG MV-90. You see, Matt, one phase has number 4 and the other 2 phases has number 2. One of them is smaller than the other. Can you guys see that? And that's okay. Now, is it okay to put all of them the same size based on the largest? Yep. What's wrong with that? You're throwing money, basically, away. Any comments, any question? Really, the tricky one is A and C size will be different than B. That's all. Because of that single phase and 3-phase load in A and C only. Should we go to 10? Any question, guys, about 9? Why 1.25? We're assuming it's continuous load. Okay, so let's go to the secondary side. The secondary side, guys, is no difference. The secondary side for A and C, let's do them for A and C first. And for A and C, I'm going to say I secondary line for A and C. Do you guys remember it was 1, what was it? 1163 or 1164 right here? The two, when we added them together on the secondary side, oops, where am I here? 931. I'm sorry, my fault. I was looking at So 931. So this one here was 931 amps. You guys remember for secondary secondary line, it was 931, right? Is that what we calculated? Then you're going to come over here, 1.25 continuous load, 931. When you guys do this math, we're going to end up with 1164 amp. 1164 amps. Any question guys about that? That's multiplication. Then what we do, guys, is we divide this by 1164, divide by 4, because this is a huge amount of current to carry, right? I'm going to parallel them three sets. I'm actually doing 3 sets. You can do 4 sets too. I'm dividing 3 sets. That'll give me 388 amps. I have 388 amps. Why did I divide by 3? Because I want to parallel. And you guys have done paralleling before. Then, gentlemen, you come over here and you take your 388 amps. You're going to take them to table 310.15 B16 under 75 degree column, because this is 240. You're going to end up with 3 sets of 2 conductors, right? Each one of them is number 600 kcm THHN. Can you guys see that? That's for phase A and B, right? Makes sense? I paralleled 3 sets. Could you have paralleled 4 sets? Yep. Your rule of thumb when you parallel what? When that number that you come up with, you will end up with close to 400. That's kind of your rule of thumb. You probably could have done 4 sets, and that's okay too. All right, let's do B. Now that's phase A. Now for phase B, gentlemen, phase B, I want to remind you for phase B, secondary line for phase B, 7723 amps, right? Then same thing, do the math. 723 multiplied by 1. Let's do it the proper way. 1.25. 1.25 times 723, assuming it's continuous load, worst scenario, I came up with 904 amps. And then you take your 904. Now, Karen, I already paralleled 3 sets, so I have to go 3 sets here. So 3 sets, almost, that'll give me 301 amps, right? And then, gentlemen, if you take it to table 310.15 B16, 75 degree column, you're going to end up with 3 sets of what? 3 sets of 301. I have 350 of 1 conductor, size 350 kcm THHN. So why 1 conductor? It's only phase B. Why 1 conductor is only phase B? Any comments, guys? Any questions? Any comments? Any questions? We're going to size and neuter in a second. Any comments about these? So you end up with one set 350 and the other one is 600. So Adam, you walk into this project and you see, my God, why are they coming to the same panel? And you're confused. Don't get confused. That's because of a system like this. Comments, question, guys? Okay, so let's go size and neutral. Remember, there is a neutral. Now, for a neutral, for the neutral guys, you could have gotten away. You can have 3 sets of 500, but obviously this is not going to be seen by the neutral. For your neutral, here's the calculation for a neutral. Neutral conductor. For the neutral conductor, guys, um, the neutral current that's going to be coming, now remember, for the neutral conductor, it's I in neutral, the worst scenario, is basically 208, right? Remember, it's 208 amps. And actually, this came from single phase. So this was coming from, let me just remind, okay, so I neutral equal to 08 amps. I'm going to remind you guys where this came from. So if you go all the way back, which step were we looking at the phase? Here you go. See, can you guys see where the 208 came from? The single phase, right here. That's for the neutral. The single phase load is the neutral, 208. Okay, so go all the way. All right, so I have my neutral is this one. Now for a neutral, we could assume it's continuous load or non-continuous load. Typically, this is assumption non-continuous load. So I need to parallel, guys. So here's my neutral load. Then I have 208. I have to parallel 3 sets because I have 3 with each. I have 3 conductors for phase A and phase B. So I have to have 1 with each one of them. So that will give me 69 amps. Cool. And then if you take 69 amps, guys, 69 amps, take it to table 310.15 B16, 75-degree column. Even if you multiply it by 1.25, which we did not, you're going to end up with 61, 75-degree column. I end up with 3 sets of 1 conductor. Each one of them has 4 AWGTHHN. Okay? Now, I want to remind you guys, can you parallel less than 1 aught? The code says you cannot parallel less than 1 aught. So, because of this, gentlemen, the size will change into, your neutral size will be 3 sets of 1 conductor, 1 aught, AWG, THHN, because of paralleling. Because of paralleling. So what happened to this baby? You cross it. Did you guys see that? Because you're paralleling atom, you can't go less than that even if you want to. Right? You can't parallel less than 1 aught. That's what the code says. I want you guys to write these so you know where we came from. Any comments, any questions about this? Why didn't I multiply by 1.25? Neutral is highly unlikely, guys. It's going to be all continuous, all fully loaded continuous. So it's going to be definitely, this is a worse scenario even. And we already went up. Okay, this is how your conduit is going to look like, guys. When you put your conduits, there will be 3 sets. Can you guys see that? So here's phase A, phase B, phase C, and a neutral. Phase A, phase B, phase C, and a neutral. And phase A, phase B, phase C, and a neutral for the 3 sets. And you can see the neutral will be 1 aught, phase B will be 350, and phase C is going to be 600. That's how your conduits are going to be loaded. Can you see that? So the 2 phases, phase A and C are the same size, B is different, and neutral is different when you size your conduits. Cool? Any comments, guys? Any questions? So that's probably the hardest one to understand. Comments, questions? So let's go to the fuse. If you guys are good with that one, that's probably the hardest one. Let's go to the fuses. For the fuses, we're going to use table 450.3a. Why A? Because one of them is higher than 600 volt, guys. And I'm not going to go to the table anymore because you guys are experts in the cable business, in the table business. So I will remind you, primary overcurrent protection device, A and C. What was the total on the primary side? So the first thing you need to do is I, primary line was 94. Was it 94? 93.3. 93.3? 93.3 amps. Okay, you might have to check that one for me. And then you take the 93.3, multiply that one by the multiplier that you can go from this table, guys. We talked about this one, 300 percentage multiplied on the primary side by 3 multiplied by 93, 93.3. So to give you something similar to, it might be up and down a little bit because I'm off a little bit, 282 amps. Then you're going to take your 282 amps, give or take, to 240.6, and you can go up. Can we go up on the primary side? You can go up, and that will get you 2 fuses. Each one of them is 300 amp. In phase A and phase C, 2 fuses. Each one of them is going to be a 200 amp. Now, gentlemen, for B, I primary line for B was only 70. What was it? 72 or 73? 73.3. 73.3 amps. And then you take your, you multiply by 300, the same thing, 300% times 73.3 amps. That will get you a healthy 219 amps. Now you take the 219 amps, same thing, you're going to take it to 240.6, gentlemen, and you get 1 fuse, and the size is 225 amp. Your size is 225 amp. So you're going to have 2 fuses the same size, and the third fuse is going to be smaller. Any problem with that? No. Any problem with that? No problem. On the primary side. In a second, we will go to the secondary side. Any comments, guys? Any questions? I can't emphasize there is, you know that the key point is to identify which current you're going to be using. Can you guys see that current and that current for each one of these? These are the ones, and then the rest is, we've done it. You have to identify which current to use for each. So the 2 phases now have 300 amp fuses, and the third phase, which is phase B, have 225. All right, shall we go to secondary, Karen? Good. Matt? Okay, the secondary, guys, same way. The first thing you need to do is identify, what was it, 931 amp? Is that the amps that we used? 931 amps. Okay, piece of cake. Then, right underneath it, I have to write here, I secondary line 931 amps. Okay, 931 amps. 125% is my multiplier from the table, and we were there. You guys should know that one. 931. If you do that, you're going to end up with 1164 amps. Cool. And then you take the 1164 amps and you go to 240.6 looking for a beautiful fuse, and that fuse will get you 2 fuses. Each one of them will be 1200 amp. You will have 2 fuses. Why 2 fuses? 1 fuse for phase A and 1 for phase C. Okay, looking at B, gentlemen, same thing for BI. Secondary line for B, 904 amps. Then you're going to take the 125%, multiply it by 904, and we know why 904 was only 904. No, this is 70. I'm sorry. This should be, I lied to you. This is should be 723. Thank you. That's why it doesn't make sense. 723, and then this is 723. Yep. Now the total will be 904. There you go. 904 amp. I'm ahead of myself. Then you take the 904 amps, guys. Take it to 240.6, and that will get you a one fuse of 1,000 amp. One fuse of 1,000 amp. So how easy that, huh? Any comments, guys? Any questions? Any comments? Any questions? Comments, questions? I cannot emphasize, Adam, that these are the key points for the solution, is to identify the current. The minute that you find the primary and the secondary line current for phase A, B, and C, then you start just multiplying them by the multipliers. A lot of mistakes, guys, is people put this one here and that one there, and you know. The steps of multiplication, please write yourself a note. Bring your code book, write in it. Gentlemen, the last step is 14. 14 is find the short circuit, short circuit on the secondary side of the transformer. The short circuit, short circuit, I secondary line plus I secondary single phase divided by the secondary. So basically, you're going to take the total I31, the worst scenario, right? 931 is the worst scenario. Divided by 3%, the impedance is 3%. Gentlemen, you got yourself a 31 kiloamp short circuit on the secondary side of this transformer. Which is basically, we used the current for phase A and phase B because that's the highest, right? That's the highest line current, is phase A and phase B. Phase A and phase C.
You don't add them together.
Well, if you add them together, you're going to end up with, this is the one that we size for phase A and phase C.
Yeah.
Right? If you add them up, you're going to end up with phase A and phase C. Why? Why? Because that's a worst scenario. Any comments, guys? Any questions? Comments, questions? So that will conclude, guys, our transformer calculation. And now, from now on, we move into a whole different topic. So hopefully that's a good review. There is one more homework, guys, for you in a second here when Derek is done with that. I'm going to give you...
Check for that secondary OC.
Right here.
Device.
Did you do that? Overcomputation device? You got that one? So, Karen, what I'm going to do, guys, I'll make copies like these for you. It makes it easier. Otherwise, if you want to draw all the stuff, it will take us all day. Is that good? And please write on it. Keep them for your record, for the test and what's not. Okay, so are you good with that?
Yeah.
Okay, so let's go down. Did you get the short circuit? Yeah. Good. Now the homework, gentlemen. Here's your homework. Homework number 2. Please, you guys have it written. We have 12.47 kVA, high voltage on the primary. In the secondary, 241.20. Center tapped system. The kVA is 200, 200, 300. So, and the impedance is 4%. And I would like you guys to do all the steps, basically step 1 through step 14 for this example. Cool? These are due next week on Monday, these two. Everybody understand the homework for these two, for the calc? This is how I'm going to do the homework for the calc, Adam. At the end of it, I will have a homework for you guys to basically go step by step, follow these, so hopefully we'll get you to exercise. Any comments, any questions, gentlemen, ladies? Okay, so what I would like guys to, this is the lecture for today. Then next I'm going to walk you through in a few how to start laying out your low voltage for the project. Thank you.